Hello everyone, welcome to my channel. In this video, we will be discussing about the design of microstrip antenna theoretical calculations for the one which we have simulated in the previous video using Keysight ADS. So, without any delay, we'll move into the further. There are 3 points to be focused. The first thing is the length and width of the patch, and the second thing is the dimensions of the quarter wave transmission line, and the third thing is the dimensions of the feed line. So if you have forgotten previous video, this is the basic idea of the antenna we designed. This we refer to as length and width of the patch. This we are referring to the dimensions of the transmission line, and the third one is the dimensions of the feed line. So to calculate length and width of the patch, this is the formula. Width is equals to C naught in by 2FR under root 2 by epsilon r plus 1. So frequency of resonance for us is 2.4 gigahertz and epsilon r is 4.4 for FR4 material, and height of the substrate we took it as 1.6 mm. So if you substitute those, you will get the width to be 38.03 mm theoretically, and in epsilon effective you will get it to be 4.08. So coming to the L effective, we have something called as 2 delta L here. What is 2 delta L is, if you consider a rectangular patch antenna, you have fringe fields along the width of the antenna or height of the antenna. So these fringe fields also will contribute to the length of the antenna. This whole thing you call it as L, but actual L effective length of the antenna, but actual length of the antenna is only this much. But you are adding this delta L to both sides of the antenna, which will result in 2 delta L. First, if we calculate only the actual length of the antenna, this will come out to be 30.944 mm, and if you calculate the 2 delta L part, this will be 1.47 mm. So actual length will be 30.94 minus 1.47, which will be approximately 29.94 minus 0.47, which will be 29.5 mm. So length is 29.5 mm, width is 38.03 mm. Once you are done with this, you can move to the calculation of microstrip transmission line. Why do we need microstrip transmission line is, if you take the antenna, if this is a rectangular patch, the impedance over here is somewhere around 200 ohms. But for any antenna or any power supply, for giving the input, we need 50 ohm resistance. So if you keep the 50 ohm impedance input to 200 ohm impedance, what happens is, due to impedance mismatch, there will be a power loss, and also you won't get the output. So to eliminate this, we use a special form of microstrip antenna whose wavelength is equals to the 1/4 of the wavelength of the wave, which is known as quarter wave transmission line. This has a special feature which is nothing but it will function as a impedance transformer also. Here Z0 will be the value like under root of from which impedance you are transforming 200 ohms into which impedance 50 ohms. So this will be 100. So for our case Z0 will be 100. If you calculate Z0 here, you will get the Z0 to be 2.899. Once you got the Z0, you can substitute the value of A in the formula to get W by H is equals to 0.4418. But we already know that H is equals to 1.6, which will result W is equals to 0.707 mm. So once you got the W, we can calculate epsilon effective, which will be 5.4 by 2 plus 3.4 by 2 into 1 plus 12 into height will be 1.6 and width will be 0.707 whole power minus 1 by 2. This will be 3.023. Now we need to calculate the length of the transmission line. So k naught is nothing but the wave number, which is 2 pi by lambda. So if you replace it, you'll get length is equals to c by 4 fr under root epsilon effective. So this will be 17.97 mm. You can calculate it. So you got length of the quarter wave transmission line, width of the quarter wave transmission line, and next the feed line. For feed line also the same thing, but only thing will change is z naught value. For feed line we'll keep it as 50. In the previous case we took it as 100. So now a value will be 1.526. If you substitute this a value 1.526 in w by h, what you will get is you will get somewhere around w by h is equals to 1, sorry, w by h is equals to 1.83 something. So we already know that h is equals to 1.6, so our w will be 2 point, yeah, let me check it once again. 1.6, yeah, 2.94. Our width will be 2.94 mm. Once you got the width, you have to calculate epsilon effective as mentioned in the previous slide. Now the epsilon effective will come out to be 3.31. 3.31. If you substitute the epsilon effective and find the length, which is L is equals to C by 4 FR under root epsilon naught, you will get length to be 17.7 mm. Now some of you who have followed my previous video might get a doubt key. In the previous video for the feed line, I took the dimensions as 3 mm into 5 mm. Actually, that is also a good practice only. We are reducing the length of the feed line. Even if you reduce the length of the feed line, the frequency won't be affected, because the frequency will only be affected by the length and width of the rectangular patch itself. This reducing the feed line will not affect any frequency. So you can either keep it to be 17.7 mm, or as mentioned in the previous video, you can also keep it to 5 mm. So coming to the final results, let us divide into three parts: rectangular patch, quarter wave transmission line, and feed line. For rectangular patch, our calculated width was 38.03 mm, 38.03 mm, and calculated length was 29.5 mm. For quarter wave transmission line, calculated width was 0.707 mm, and calculated length was 17.97 mm. For feed line, the calculated width was 2.94 mm and calculated length was 17.7 mm. So these are the theoretical values of the theoretical dimensions of the microstrip antenna that we designed in the previous video. If any one of you have any doubts regarding theoretical calculations, can comment below this video. I'll respond. If you find this video informative and useful, please do share this video with your friends. Like the video and subscribe to my channel Tech Talks. Thank you.